Let's try this again. Good morning, everyone. So we're really excited to provide this overview today, the ad hoc technical team analysis related to impacts of growth and climate change on water supply reliability and fisheries health, river health. This work has been going on for several months now. It's a direct result of Water Forum member interest in understanding the impacts of climate change, and specifically the gaps that we're likely to anticipate in this region. And there's a lot in here. So let's get started. Go ahead. So I'm going to talk through just a little bit of the executive summary, just the bottom line, what we're seeing as the major points. And then Ashley and Jeff are going to walk us through the deep dive on the study. We're going to talk a little bit at the end about implications and next steps, and we'll go from there. We'll take a little bit of a break after that as well. Okay, go ahead. Go ahead. All right, so those of you, you've all been really involved and engaged in the Water Forum 2.0 process for about 2 years now. And I just want to say that this the ad hoc tech team and this gap analysis, it was very present in phase 2. The majority of the work was done in phase 2. Thanks, Ashley, to be able to show. Yep, right in the middle. And it's really an outgrowth of an interest and really trying to dig in on key management questions and doing a study plan analysis, which was in phase 1. And I just have to say that we're at a point now in phase 3 where the technical analysis is starting to come together with the interest statements, the planning work that we've been doing, and we are getting to a place where we will be moving in phase 3 into discussions and negotiations. And we're going to talk more about the working group structure and what those negotiations might look like. But for the purposes of this presentation, I think it's really important for all of us to really dig in. So to the extent possible, put all your distractions aside. This is not as data heavy as, we have a more data heavy version of this, so we can get way into the details, but really the goal of this presentation is that all of us sitting here, no matter our level of technical expertise or a range of technical expertise, that we're all coming away from this presentation with a really strong understanding of what the impacts are that we need to be looking at and that we need to be negotiating. So go ahead, next slide. Just a minute on the ad hoc technical team. It was formed by the Negotiating Steering Committee, which is the Water Forum 2.0 group that is helping guide this process. The goal was really to inform an approach and help translate sort of the analysis of that study plan modeling work into a basis for a Water Forum 2.0 negotiations. So Jeff and Ashley are going to talk more about what the outcomes are from this process. And I have to say, one, just a huge amount of appreciation for the ad hoc tech team members. There were a lot of hours that went into this, a lot of review of modeling results, discussion, a lot of thinking about how this technical information and translate it so that it makes sense for all of us and that it's accessible for all of us in the negotiations. So just really quick, ad hoc tech team members, can you raise your hand and let us give you a little bit of a shout out? Ron, Jim Ray, yep. Jeff and Ashley, help me here. Chris Brown, yep.
Clyde and Ron,
yep.
Mike Grinstead, Rob Schwartz, Gary Bardini and Ansel, yeah.
Yep.
Ted Rao.
Ted Rao. Yep. Thank you, all of you, for your time and energy and effort going into this. Okay, next slide. Okay, here we go, bottom line.
Yep, and as we go into this, I'm just going to throw out there that some of you have seen these at the NSC, some of you will be seeing these for the first time. This is to give you an indication of what's to come in the rest of the presentation, and we would like to hold questions or comments as we go through this until we get to those sections. So go ahead, Jessica.
Yeah, thanks, Ashley. Okay, so what we're going to walk through now is really the information that will be really the high level synthesis of the ad hoc tech team analysis. So let me launch into it. Okay, so one key point, there's three key points here, and you can reference the fact sheet as well. But one, multi-year droughts are expected to become more frequent and more severe. I think this is something that we know, we've heard. There's other studies that verify this. Go ahead. But as a result of the ad hoc tech team analysis, I think we are starting to identify what implications are as well. So region being will be more likely be in drought response mode more frequently. We're going to be, what was previously sort of an infrequent or extreme event is going to be much more common. And then our operations will likely be ineffective under future hydrology due to shifts in quantity and timing, meaning what we're looking at in the future on multi-year droughts, it's that much more frequent. And I keep trying to come up with a bad analogy about that umbrella in the back of your closet and how you're actually just not ever going to need to take it out again, but we haven't figured that one out yet. So, okay, next one, surface supply reliability. Is predicted to be reduced under future conditions, which increases dependence on groundwater. Ashley and Jeff are going to walk through this in more detail. You go ahead. But what that means is that there's, with our two main supplies in the region, when surface water availability is reduced, we're going to have flexibility elsewhere. Increased frequency of low storage and Folsom is also going to be a challenge, and continuing our very active sustainable groundwater management is going to be incredibly important for the region. Okay, and then third main point, future conditions will likely result in river temperatures that make salmonid survival challenging. So the Water Forum, in this process, we're looking at river conditions overall. A portion of that is looking at fisheries conditions. A portion of that is looking at non-fisheries conditions. Right now, what we'll talk about today in the study is fisheries results, and then we'll have additional detail later on non-fisheries specific results. Go ahead. So implications, actions, balancing the beneficial uses of surface water is going to be necessary. We know we'll have to adapt and adjust to this as we go. Okay, I'm going to stop there. In terms of other studies, I mean, these are not, when you take all of this information and kind of boil it down or, bring it up to this level, it's like, of course we know that this is happening. Of course, we know multi-year droughts are going to be more frequent, more severe. What we're going to do is we're going to walk through the details and the analysis that goes with them. And I think I just want to mention there are a lot of other studies that are out there. For any of you that attended the policymakers briefing yesterday on the American River Basin study, one, it was an excellent presentation. So congrats to that whole team that put that together. Two, it is recorded. If you have not listened to it, I highly encourage it. And we'll throw the link in the chat. But that study has really helped further the understanding of this region and climate change impacts. And our work does use data from the basin study as a foundation, and it applies it to these analysis tools to really make sure that it's tailored. And I want to say that Water Forum's work is, we are providing a cross-check on this existing information and research that's out there. And really the study that you're going to hear about today is taking this information and really customizing it for what we're about to drop into in terms of negotiations. So it's all of this information, but thinking through it in the perspective of the co-equal objectives. So water supply reliability and fisheries conditions, or excuse me, river conditions. Okay, so I would just say when we get through, by the time you're through this presentation, our hope is just that we all have a shared understanding about the magnitude of the problems that we're facing. It's the good news is that this analysis, it provides a foundation for developing some of the strategies that we're going to need. And here we go. Okay, Ashley, did I miss anything? Okay.
Nope. Yeah, and I think, yeah, Jeff will just add a little bit more detail in terms of the other studies,
Mhm.
and but yeah, well, that's perfect.
Okay. Sounds good. All right, Jeff,
Thanks,
take it
Jess.
away.
I don't have a whole lot to add other than, these studies did come out recently. So Paula just dropped in the chat about the Delta Conveyance Project, DEIR. So, the analysis we did is, as Jessica said, uses the hydrology from the American River Basin study, that they provided that to us, and we were able to use it for our purposes. But at a base level, a lot of the modeling that we did is has some different assumptions than the basin study, and I would characterize it at a certain level as an evolution. What we have is a little more current in terms of system representation and a number of different elements, and we can talk about that in more detail later. We haven't done direct comparisons against the basin study, and we intend to. We will. It just as people know, it did just come out as very much emerging science, emerging information, and frankly, we didn't know when it would be coming out, so we haven't done the detailed review. I think that we are generally consistent with what it shows, at least with for the no project conditions. For the GSPs, again, similar type of thing that they do representation of sustainable groundwater operations and management within the basin. With the modeling that we did for this, it takes a slightly different approach to groundwater management. And so we're using those GSPs as a data point and as a reference for our analyses, but they do include fundamentally different assumptions in how the analyses were conducted. So direct side-by-side comparison isn't necessarily appropriate or applicable. But we will, like I said, continue to use those as reference points. I think that's all I got for this one. You want me to get into this one? Or are you gonna
Yeah.
The deep dive. Go ahead, Ashley.
Yeah, no, so like Jessica talked about at the beginning, appreciate her giving that executive summary, the high level overview of the takeaways and implications. Now we're going to be getting into more of the details of the study plan and the findings of the ad hoc tech team. So we'll include some of the just high level science behind the study. We won't get into a lot of the details there. And then we'll walk through each of those 3 points that Jessica mentioned at the beginning with the hydrology summary, water supply reliability, and river health. So we'll be walking through those in more detail and looking at the data that supports those takeaways and implications. I'm going to let Jeff talk about the science behind the study and some of the modeling and the assumptions, and then I'll come back for a discussion on the findings. And you're on mute, Jeff.
Sorry. Is there another click? Okay, so basically what we're doing is trying to develop some modeling to represent the current. We develop a kind of a basis of comparison representing current conditions, and then looking to develop some scenarios that would let us look at, in some ways, both isolate the effects of growth and then also understand the effects of climate change. So what we've got is 4 scenarios here. We have a current conditions, which is using current level demands and a current representation of hydrology. We have a projected growth scenario, which is using projected. Just the only change is it has 2040 level demands, and then we have 2 climate change scenarios, which also layer on different hydrologies. So for these, and it says here in the note that 2020 and the 2040 demands come from the 2020 urban water management plans. So that was an effort that we went through to update those demands based on everyone's published values. And then we took the basin study hydrology, developed these 2 climate change scenarios. So for just as we want to conduct analyses, we would to evaluate the effects of growth, we would compare that second scenario with the first scenario, and any differences between the model results would show just the effects of growth. And then if we compared that projected growth scenario to the 2 climate change scenarios, we'd be able to isolate the effects of climate change on conditions. And we do have 2 different climate change scenarios. We have this moderate and a severe, and those they'll be reflected in the results, that the differences between those 2. The way I would characterize it is that the moderate version focuses primarily on a change of timing for the hydrology. The overall annual magnitude doesn't change a whole lot, whereas the severe version does have both a reduction in annual volume and a change in timing. We use two models to do this analysis. The first is calcium 3. Calcium 3 was used for the Delta Conveyance Plan DEIR that just came out. It was used for the basin study. It's a widely used model platform developed by the state and Bureau of Reclamation. It represents the full CVP and SWP systems and how they interact, how they meet their combined objectives within the Delta, how they deliver water throughout the state. And we need that to be able to understand how Folsom's operation, Folsom doesn't operate in just for the American River needs. It's part of the larger integrated system. So we needed to use a statewide model to understand Folsom's operations beyond just the local needs. Then we used a model called HEC 5Q. It's a water temperature model that we use that to evaluate the effects of the calcium 3 scenarios on American River water temperatures. So that model includes Folsom Reservoir and then the lower American River. And so we can see how changes in Folsom storage and Folsom releases affect both the cold water pool development within the reservoir and downstream. The HEC 5Q is the model that was used for the Delta Conveyance Plan that they have. I was just given the model by DWR a couple days ago. I haven't done a deep review of it, but reading the literature, it cites that it's based upon the Bureau of Reclamation model, which is the same one we use. So I anticipate that what we use is very, very similar, if not identical, to what the Delta Conveyance Plan just used for their temperature modeling. Yep. So those are. I think that's all I got for this one. So yeah, thank you.
Okay.
Ash. So one other little point did want to mention here is that where we are today, so that if you look at the third bar from the left or second one from the right, there's the actual demand for 2020. That it is higher than was anticipated when the original water forum agreement was developed, back in 1995. You can see that the demand since 1995 have gone up. But what the demands that were actually anticipated in the original water forum agreement for 2030, we have not reached that yet. And our projected 2040 demands are still short of what that 2030 demand. So this is part of, I think, well, I'll let Jessica Ashley talk about the implications to this, but really what it shows is that we're evolving in our projections and what our expectation is for water use within the basin. And I think that part of that is the response to recent droughts and how our overall water management strategies within the basin have adapted. Any more implications to that
No, the only other thing I would add is just that also the reminder that projections are estimates of the future, and that we have numbers associated with them, 2040, 2050, but they are estimates and there's uncertainty that are inherent in those estimates. And so it's one, to Jeff's point, that these projections have evolved and are not as expected 20 years ago. And that the same might be true in 20 years, that those projections may be over, under, and just to keep that in mind as we go through these results, in that projections are estimates and not predictive.
And one thing, we attach a year to this. This is not to say that that's the expectation for 2040 and that 2041, it would have been a little bit higher, and 2039 would have been a little lower.
Right.
It's just, this is a 2040 era type projection. And same thing with the hydrology. We refer to it as a 2050 hydrology. But if you look within the basin study, it actually calls it I think it's a 2035 to 2065 hydrology. So it's representative of somewhere in that range. It's not exactly at 2050. So, we attach a year to these, but that's not to say that that is the exact specific year that we expect this to manifest.
Right. Okay. So with that, we're going to start looking at these results in these three different categories. Thank you, Jeff and Jessica. And as we go through these, I'm going to go through each of the three sections, and we're going to ask I'll go all the way through, like in this case, the changing hydrology, and to hold questions or comments until I get all the way through. And then when we get through, we'll have a place to pause and ask questions, comments, clarifications. So going into the changing hydrology, These are building off of the executive summary takeaways that were shared at the beginning. But some of the takeaways from the data are that the runoff peaks are estimated to shift earlier. The frequency of dry and critical years are estimated to increase, and that those multi-year droughts are estimated to be more severe and frequent in the future. And just to say that looking at this hydrology is essentially looking at what we're only looking at the climate change scenarios in this case and looking at how those hydrologies will change, and not yet looking at how the system would respond to these changing patterns in hydrology. So to that first point, the runoff peaks are estimated to shift earlier. This is a chart, and I think a lot of you have probably seen different versions of this type of information and indicating how those runoff patterns are expected to shift in the future due to climate change. So this first chart is showing the average peak runoff for the entire scenario for both the 2020, the central tendency, and the hotter, drier scenario. And where those, so when that peak monthly runoff happens within the year. So the solid line is the 2020 hydrology, and then these dashed lines represent the climate change. And so what you see with between, at least on average, between the central tendency and the hotter, drier, even though they are different hydrologies, that trend in when those hydrologies peak is very similar, regardless of the scenario you're looking at. And on average, that peak is coming 2 months earlier. One of the points we wanted to highlight here, though, is that that's average. That's looking at all of the 94 years of the simulation. And when you look at the different water year types, so looking at wet years, dry years, critical years, it varies. And basically it's very accentuated in the wet years. That peak is much earlier, to where it's coming 4 months earlier as opposed to the 2020 hydrology. So shifting all the way back to mid-January, and then whereas now under 2020, it's expected to come in May. And what this is indicative of is that lost snowpack that I think a lot of us have been hearing about, is that those storm events are not coming in the form that they used to, with snow falling up in the Sierras, and it's coming more as precipitation, and all that runoff is coming into the reservoirs much earlier. And this trend, if we were to look at the other years, wet, above normal, dry, critical, that peak gets closer and closer, but on average, it's about 2 months, with the wet years being more accentuated. In terms of and then thinking about the frequency of the dry and critical years across the different hydrologies, this is just a really simple breakdown of how those different what's the composition of those different hydrologies. So under 2020, looking at how they're categorized between critical, wet, above normal, below normal, and dry. And you see that breakdown. And then when you get to the 2050 central tendency, it's not a large change, but it is a 3% increase in the number of critical years, and a 5% decrease in the number of wet years, where that trend gets really accentuated when we move into the hotter, drier, and that the critical years are doubled in frequency and the wet years are halved. And then in addition to that these dry and critical years are almost 60% of the simulation period. And so if we look at the 2050 hydrology, the hotter, drier hydrology, those dry and critical years become a lot more frequent than we have seen them under the current hydrologic trends. And just to pause for a second and note when we're talking about central tendency and hotter, drier, Jeff talked a little bit about this in the beginning of the presentation, but just to say that I won't be able to get into the real technical details. I'm not a climate scientist. Jeff can go into more detail than I can. So if we have more questions, just let us know. But what I can say is that there are different trajectories for the climate based on global climate models, with warming to varying degrees, precipitation changing to varying degrees, and different horizons for projecting those based on CO2 emissions. The central tendency is exactly what it sounds like. It's a central tendency kind of averaging those trends between temperature and precipitation. The hotter, drier is leaning towards the warmer and the drier trends. Hopefully that helps. I don't know if Jeff, you would like to add or clarify anything I just said.
I mean, I just, without going into a ton of detail, and happy to have a longer discussion about it, or you could check out the Basin Study report. They have a pretty detailed appendix about the climatology used. but basically that that central tendency is kind of a median increase in precipitation, a median change in temperature, whereas the hotter drier is both a 90% exceedance of the precipitation, whereas of all the different climate models, 90% of them would have more precipitation. So this is down in the lowest 10% of precipitation, and it's a 10% or also the 10% exceedance on the temperature. So only 10% of the years would be hotter. So it's on the extreme of the hottest and the extreme of the, or towards the extreme of the hottest, towards the extreme of the driest. And so that it's not the hottest, not the driest, but it's in that of the temperature models of the climate models that were used, it's in that quadrant. So hopefully that helps a little bit.
Yep, thanks, Jeff. Okay, so then looking at the third point here for the changing hydrology, that the multi-year droughts are estimated to be more frequent and more severe. Trying to find a way to communicate and capture this was a bit of a challenge. So we're hoping that this will help punctuate and show that estimate and that projection. So this table on the right, what we're looking at is for historical runoff and historical precipitation, what the average amount of runoff, cumulative runoff for the watershed is for this period. So with 1 year down to 6 years. So ranging it from about 2 million up to about 15 million acre feet, 15 million acre feet within that period. And so then looking at the hydrologies used for our simulation and we want to look at the driest period for each of these durations. So the blue line is showing you the absolute driest within the 2020 hydrology for each of these different durations. So a 6-year drought and a 2-year drought, and looking at what that totals to. So thinking about the 1-year drought being, I think like 400,000, or I'm sorry, yeah, that's right. Let me think. Yeah, right, 400,000 acre feet, got it. But the 1-year average being about 2 million acre feet. So that's a very dry year. And looking at the central tendency and the hotter drier, the central tendency is actually that lowest period is a little bit higher. There's not a lot of change. But if we shift over here to the 4-year drought cycle, this is showing you that 2020 low point, and what this corresponds to is the 2012 drought cycle, 2012 to 2015, and then looking at the central tendency and the hotter drier and seeing how many, if and how many there were cycles within that hydrology that were less than or equal to that 2020 projection or estimate. And so you see that under the central tendency, there's one cycle that is less than, but it's only one, and it is less, but a slight shift over a 4-year period. But when we look at the hotter drier, there are significantly more cycles that are equal or greater, or equal or less than that 2020 low point. And essentially there were 10 events where the 4-year cumulative runoff was less than that 2012-2015 point of reference. And then just looking at how those trends compare across those different drought cycles. So the orange bar is indicating that there are more periods at that 2020 low point, and that when you look at the absolute driest, especially in this 4-year cycle, it is a significant amount of difference in the total runoff in that 4-year cycle. So the droughts would be more frequent and more severe. So the simulation period shows less runoff, and that threshold being met more often. Tony, I see your hand. I'm going to go ahead and talk through the implications of what we just looked at for the hydrology, and then ask for questions or comments. So I'm just going to hit this last slide, and then we'll open it up. So looking at those kind of 3 points and what the implications are for the region, the region, like Jessica shared at the beginning, will be in drought response mode more frequently. What we've experienced as infrequent or extreme events will become more common. And that the current operations as they are now will likely be ineffective under that current hydrology due to the shifts in quantities and timings. So with that, I'd like to pause, but because then from here we'll move into the water supply reliability and ask for questions or comments. And Tony, do you still want to, you put your hand down, but okay.
Can you go back?
Yes.
I'm sorry, I didn't understand this, and
That's
and
okay.
it seems important, and I feel like if maybe we all need to make sure we understand it. So
Mhm.
can you maybe explain this a little differently? Did you, out of 100 years of record, did you go and pluck dry years, and that's what these bars are? Is each one is one of the dry years out of 100 years of record, and you're just what's the trend you're showing? So I think you need,
Yes.
for me, I need you to explain this a little more. I'm not sure.
Okay. I'll try a different way, and then if that helps, that's great. And if not, maybe Jeff can step in and try his way too. So the within that, I think it's 94 years of simulation. We looked at the 2020 first and found what the lowest, the driest period was for each of these durations below. So 2-year, 3-year, 4-year. Where in that 20-year simulation was the absolute driest cycle of that duration. And then we looked into the central tendency and the hotter drier and found all of the cycles that were at that threshold or lower. So it's looking at essentially what was the one and only driest period of that drought spell, and then found how often and how much worse were similar drought spells in the other hydrologies. Is that?
Or maybe said another way, we accumulated for the full 93 years. So looked at and accumulated the 1, 2, 3, 4, 5, 6, all the different periods that would over 1 year, over 2 years. This is based on the unimpaired flow at Folsom Reservoir. So looked at what's the cumulative 1 year unimpaired flow volume. Well, it was 1977 for all 3 scenarios. And we looked at the cumulative 2-year unimpaired flow volume, cumulative 3-year, and just ranked them all out for each different hydrology, and then compared to how many were equal to or less than the 2020 hydrology. So that's what this represents here.
Yep. Thanks, Jeff.
Yes. So that is not a, yeah. So yeah, and you can compare the table on the right shows what the average, if you again look at those. This is based on historical on the right. This is not model data. This is the historical unimpaired flow. And the accumulative 1 year, 2 year, 3 year, 4 year, 5 year, 6 year accumulated unimpaired flow volume. And what was the average over that same period of record?
Yeah. So hopefully that helped, Tony. I see you nodding, so that's a good sign. Go ahead, Paul.
I'm confused as to how the table and the chart relate to each other. So take an example here. The y-axis on the chart is cumulative runoff, 1,000 acre feet. So for the 4-year group there, you've got 2020, and it's somewhere around 5 million acre feet, right?
Over here. Yes.
Yeah.
Okay. But that's cumulative runoff. So how does that 5 million acre feet compare to the 10 million acre feet in the 4-year duration row for the historical average?
That 10 million acre feet is the historical average of the cumulative runoff. Okay,
so why is the column there for 2020? Is that not the historical average? What is that column there?
That's the driest 4-year period. That's the lowest. That's the lowest cumulative runoff. So that's the 2012 to 2015 period that Ashley mentioned. So that's in 2012 to 2015, the runoff was just less than 5 million acre feet. Historically, the average runoff for 4 years has been over 10 million acre feet. So that period had less than half of the historical runoff that we would expect to see over a 4-year period.
Okay, and then using the 2050 hotter, drier scenario, you're showing here that you've got 10 events that have those 4-year cumulative total runoff is what that's showing. It's not necessarily the lowest from that model, but it's just a set of 10 events that are lower than the lowest in the 2020 model.
That's right. So the single lowest in the 2050 hotter, drier would be that one over there. Yeah, that Ashley is pointing to. And so what we looked at were the 10 events that were lower than the current, than the 2020 hydrology, driest. So there were 10 events in the 2050 hotter, drier hydrology that had less runoff than, our representative current conditions scenario.
Mhm.
Okay, thanks.
So Jeff and Ashley and folks, I just want to hit pause for a second here. One, this is important for all of us to like have that aha moment. So if you're like, not getting this, we'll stay here until like there's sort of a collective understanding. There's two things that are going on in this chart. One, it's describing the frequency of droughts. And two, it's describing the severity. And so the frequency increases under climate change. If we just look at growth and demand in the region, not even looking at that. If we're just looking at sort of current conditions, the frequency of these multi-year droughts doesn't increase. When we start to look at climate change, both the central tendency and the hotter, drier, so sort of middle of the line climate change projections and extreme climate change projections, that's where you see the frequency jump up. So we're going to have more, and I'm still going to work on my umbrella analogy, but it means that we're not just going to have a 2014 to 2016 drought once in a 10-year period. We're going to have it that much more frequently. So that's the one piece, the frequency, and then the severity is also another sort of separate piece of it. So I don't know if that's helpful, but let's keep going through questions. And hopefully we can get some collective aha moments of what this means.
Thanks, Jessica. Go ahead, Rob.
Just a quick question. I'm assuming that for the multi-year droughts, they are 4 completely separate years. You don't have any overlapping years of droughts that you have, like a 20 to 24 and a 22 to 26 drought period that overlap in years. They're totally separate in the years that you've identified.
That's a really good question. And I will try to articulate this. This is essentially looking within each year of the simulation. I guess the quick answer is they are not completely separate. There is overlap. Each of these points represents a year in which that cumulative 4-year or 5-year or 6-year total was at this level. So it is a little challenging. I don't know if you want to add to that, Jeff.
Yeah. So yeah, your assumption is 180 off. So there are, if we look at, for example, that 4-year, and this is something we really struggled with trying to interpret. And I think you're capturing a very important point there, is that, for example, we had a really bad 7-year drought, 1987 to 1992. Well, you could pick out 3 different 4-year periods within that 7 years that under the hotter, drier were worse than what we experienced or what the 2012 to 2015 hydrology were. So it could be 1987, 88, 89, 90 was worse. I mean, it's like it's the 4-year cycles ending in like 89, 90, and 92, I think, or something like that. The 3 4-year cycles that were all that are worse. So it's we didn't want to exclude them, but on the same hand, it's an important point that there are, in particular for the 87 to 92 drought, there are multiple events represented in that 4-year period.
It's a low 2-year, it's a 2-year low, it's a 3-year low, it's a 4-year low. Like
So it might be worthwhile to note that as an asterisk or something on the table.
Thank you. Okay, Mike.
So I lowered my hand because Rob asked almost the exact question I was going to ask, because I think that that context is really important, that there can be overlapping years. But I had the privilege of seeing this slide in an ad hoc meeting, a version of it, and we had a lot of discussion on it. I think it was smart that the group kept it in, but I also think that it's difficult, right? That if you look at the table with the duration on the right, you have to compare the 3-year with the 3-year on the left and only the 3-year, and then you're getting an average of all the years rather than an average of the driest 3, and that can be really difficult. But if you can get through that, I think what the team is telling us is that there are some lessons to be learned there, and hopefully folks are feeling like they're starting to understand that what that means and how that works. So anyway, I like the thing. I know it's complicated, but I think we got a lot of smart people here who can get through that and connect the dots.
And I'll say we tried to put that table on the main figure as a line kind of showing what that average was, but then the problem is that you have that 60 or 15 million acre feet, and it just really wipes out all the resolution down to the lower levels. So we figured out that, well, let's just, we'll put this as a table off to the side.
All right.
Ashley, if I can just jump in, I just want to say, Mike, thank you for that. And it's always a challenge to get graphics that completely convey these really, really sort of detailed results. And Ashley, can you just go back one slide more too? Because if you ignore the volumes and the details and just see, so the frequency is really important to keep in mind here. And so that circle where critical years doubled compared to the 2020 hydrology, and then dry years, if you just look at the orange and the red and the amount of space that's taking up in the pie versus where we are now, that on just a really basic visual level, hopefully can convey the amount of swing and shift that we're going to have towards a much more critical and dry year paradigm. So yeah, I'll stop there. Yeah.
Thanks, Jessica.
Jessica,
Matt?
you said that we are going to have, I think what you meant was in that model, that's what the model is projecting.
Yes.
The central tendency model might actually be what we might have. Who knows? Right.
Exactly. And Ron, thank you. Yep. These are all predictive results.
All estimates of the future. Go ahead, Max.
Yeah, thanks, Ashley. Can you go advance one slide further back to the same chart? I think I'm gonna maybe propose another way we look at this as well. And another interpretation is if your agency was maybe planning a 3-year drought cycle, of that's how you planned your water supplies, the results from the hot, dry scenario is telling us maybe you should increase that to a 4 or 5 or 6-year drought planning cycle, because we're seeing more of these long periods of sustained drought, and also just in quantity as well. So maybe that's another way for someone to think about this, is we're seeing higher frequency of these 4 or 5 year events. Maybe the drought horizon should be expanded to look at longer drought periods as well.
Yeah, that's a helpful way to look at it also. Thank you. Bill?
It would help me from a context standpoint if we also would include just the average runoff, so that we can compare these drought, annual runoffs to just an average annual runoff.
Yeah, and we have that here. I think we need to make sure we call it out sufficiently, but this 1 year is the average annual runoff for a single year, about 2.3 million acre feet.
That's for a 1 year drought, or for just a total average?
Just total average. Yeah.
See, that doesn't make sense to me. Is this
that's where I think we need to make sure we adequately specify what we're showing. And so this is looking at the historical average runoff within the historical hydrology. But the chart on the left is showing something different. This is showing the very dry years.
Okay, so the 6 year, 5 year, those runoffs are for the total drought time.
Correct.
On the left, yes.
Okay.
Yep.
Yeah.
Those aren't per year.
Right.
Okay, so the 1 year is okay.
Yeah.
All right.
Good question, Belle. Thank you. Jim?
Well, I still am not sure that
Oh, that's okay.
Yeah, it might help actually if you actually did a per year runoff scenario and just had that number divided for each of these years. Because I see now what you're saying. I see but I can also see how this is confusing, because you're showing all those and it's not divided by the number of years, right?
Right. Right.
It just seems counterintuitive. So I must not be understanding that a 2-year drought would have a larger average annual runoff, according to the table on the right, than your 1 year.
But it's not, if you divide it by 2, then it's
I know
less.
it's still 2,600 versus 2,300.
Oh yeah, you're right. But yeah,
So that seems way counterintuitive to
then
me.
the 3 would be whatever that is divided by 3. So
That's
maybe it is
2,500.
It's not what these numbers here are not showing just like additive, like if we look at a single year average, multiplying by 6 to get the 6-year average, it's looking at the hydrology and saying for each 6-year cycle, what is that average runoff? And so the change from this 1 year historical average runoff to the 2-year is just saying that, I don't know how to articulate that, but it's not additive.
Yeah.
This table is not additive.
I know it's not additive, but are you sure the 1 year, that top on the right, that doesn't represent a 1 year drought?
No,
No.
but hey, Ashley, can I try this? Because it's
Yes.
the same question I tried to get us to add to this slide.
Yeah.
What you need to do, Bill, is you need to look at the table on the right are not droughts. Those are just average of the 94-year
Okay.
period of record. But if you take the orange bars or the gray bar and you divide it, like Chris was saying, divide the 4-year 5 million thousand acre feet, 5 million acre feet, divided by 4, you get, 1,250 acre feet per year. So that's the average in those 4 years. Each year has only 1,250,000 acre feet.
For 4 years consecutively.
Over 4 years,
Mhm.
you have to divide, like Chris was saying, divide the orange bars by 3, 4, 5, or 6, and you'll get something that's comparable to the average to those years. If you do the same thing in the blue chart, divide it by 2, 3, 4, 5, or 6. And then I think you'd see what a drought looks like compared to the average.
Okay, that's helpful. Just it still seems counterintuitive to me that, well, I guess I don't understand why they're on the table to the right. Why is there a difference between a 1 year average runoff and a 2 year average runoff? And why would the 2 year average runoff be more than the annual than the 1 year?
One thing that might help, those are actually medians as well. So it's not, I labeled it as average, but it's actually median. So that might change things a little bit, but it has to do with the distribution of how those 2 years work out. And so, yeah, you just can't necessarily add them all up.
Right.
Yeah.
Interesting.
Happy to publish the data. We'll put it on the website if you're interested.
it all seems to average around 25 or 2,600, except for that first year, on a per year basis.
By the way, I love the slide.
I did too.
And luckily, I think this is the most complicated one to wrap our heads around. So just know it's going to get easier. And this is, yeah, I appreciate all of this because I think it is important that we all can come away with an understanding of this. So go ahead, Tony.
I'm starting to feel like I'm back in like high school algebra and grilling the professor and not getting past the problem until I understand it. That's okay. So what I love is the attempt to make apparent the cumulative effects of dry years on all of our interests. And that's what this is all about, right? Because so often all we do is talk about a drought year.
Right.
And the point is that we also need to be talking about drought epics, right? Things that go on for years. And so I'll leave it to all of you to figure out how to deal with the making this a little bit more intuitive mathematically. But I do have a suggestion. And the suggestion is that we have enough observation of dry years to know when bad things happen, right? We've got, in fact, even in the water form agreement, we have years where we operate differently because of concerns to the environment and things like that. And so something that would help me is to incorporate into this, when do we exceed those thresholds in these multi-year periods, in these multi-year episodes? Because what that can start to visualize for us is that, we're going to have 4 years where we're operating below 900,000 acre feet of runoff or something like that. And now all of a sudden I start to have an appreciation for what we're up against. And so some attempt to put thresholds in here would help me. And I too think it can be a good slide. We just need to learn to understand it.
Mm-hmm.
Thank you.
Thank you, Tony. Holger?
I was just wondering if we knew what the mean was for the 94-year modeling cycle. I mean, how does that compare to the 1 year average?
Good question. I bet you Jeff could answer that in about one minute.
Yeah, the average. So let's talk about median. So the median over the modeled period of record for the 2020 hydrology is 2.3. So it's really close.
Mm-hmm.
Or 2.25. So yeah. So it's they're within spitting distance.
And just to say that the 2020 hydrology that's in the model is intended to represent the historical hydrology. It's I want to say synthetic version of it in order to feed it into calcium. But the attempt is to match historical hydrologies.
Well, Holger, your question was, what's the mean versus the median? Is that what you were asking?
Yes.
Oh, I'm sorry. So the average the average in the model, I'll calculate that one real quick. For a single year, the average is 2.5 million. The average historical for the same period was about 2.5 million. So the median is slightly less than the average.
Okay.
And just for anybody, quick note: median versus mean, Jeff.
Yeah. Oh, sorry. So I think everyone's familiar with the concept of average. Just add everything up, then divide by the total number.
Mm-hmm.
Whereas median is what is the value that is in the middle. That half of the value, half of the members of the data set are greater and half are less. So it's the middle value.
Yeah.
And so what the average does is it provides weighting to values that are either really large or really small.
Mm-hmm.
And so median kind of just treats everything. You could have half of them could be very, very, very large values and half could be very, very small. And it's just going to say, this is what is in the middle,
Yeah.
just the middle value of all the values.
So Jeff, are you gonna rename the historical average?
Yes.
Or you send this out?
Yeah.
Thank you.
Paul?
I'm sorry, maybe that's the answer to my question. So the table is not the actual historical median?
It's the historical median.
It is
But
the
not,
historical.
but not the
Okay.
historical average.
Right.
No, okay, so it's the median, but I thought you said, Jeff, that the historical median for 1 year was 2.25. Why is it listed here?
That was the model, the 2020 model hydrology.
Let's
Okay.
go ahead and move on, because now we're throwing out verbal numbers that aren't on the slide, and we're going to get woof. And so let's move on. But I think that we, at least hopefully, we're all coming away with this understanding that the droughts are anticipated to be more frequent and more severe. How we communicate that, we will continue to refine. So, and then the takeaways for the implications for the region. If everyone is okay, moving on from the hydrology, we can get into the water supply reliability. So the takeaways from the data from yeah.
Ashley, can I just interrupt for 1 second? Because I just want to capture that this is like fabulous water forum style discussion here. The fact that everyone's pitching in, and I really appreciate the conversation around really trying to understand what this says, what these charts say, what are the implications, and to the extent that you're all jumping in and saying, and this is how I see it, or this is what the implications are to me, or this is how I'm imagining it. That's really good. Let's, as we walk through these next two, let's continue to do that and have that kind of a conversation. And there's also going to be a report that comes out that will provide a lot more detail.
Yes. Yeah. And we'll talk about that in next steps too. This is, again, just reminding, this is a high level summary of the data and the implications, and there's more to it, there's more data, and we can get into more of that at different phases. So the takeaways from the data related to water supply reliability are that climate change increases the frequency of critically low storage at Folsom Reservoir. Growth results in increased surface water diversions. Climate change decreases surface water supply availability and increases that variability between different water year types. And that growth and climate change both increase demand for groundwater. I think a lot of these are probably intuitive to a lot of you on the call, but we're going to just walk through some of the data that puts a little bit more meat around these statements. So when we look at Folsom storage under these future scenarios that we represented, and so now you're going to see we're getting into the scenarios that Jeff mentioned at the beginning. So those the data and the kind of the assumptions for each of the scenarios are on the top of each slide for reference. But it's again, current conditions, projected growth, moderate and severe climate change. What these two basically clusterings of bar charts are showing us are those frequencies of what are critically low storage in terms of water supply reliability. So one being December storage less than 230,000 acre feet, and the other one is frequency of September storage less than 120,000 acre feet. And so when you look at current conditions, you don't see that happening. When you look at changes due to future growth, again, you don't see that happening. Those critically low thresholds aren't being met in the model. But when we layer in climate change and that like the other slides we're looking at, and that hydrology shifts, you see a marked increase in how often that's happening with the moderate climate change scenario around 2-3% for that low December storage, and just maybe 4.5% for September storage below 120,000 acre feet, with the hotter, drier, severe climate change showing a very high frequency of occurrence for both of these thresholds. And just for anybody that's not familiar, this 230 is a target that the region strives for under dry and critical years for December storage. And then this 120,000 acre feet in Folsom is a storage at which the municipal intakes become challenging, and I don't want to say threatened, but it's getting dangerously close to dead pool, and operations will become challenging.
And that's not just September, every month.
Yes.
We use September as our indicator here.
Yep, September is a month in which storage is often at a low point before the new water year begins.
And you can say threatened.
Threatened, okay, thank you.
It's an appropriate word.
Okay. Holger, I see your hand. I'm going to go ahead and just hit these next few slides, and then we'll do questions at the end. So moving from there, so that's looking at storage, and then looking at water supply, or surface water supply, surface water diversions. And so looking at how we've looked at the hydrology and those inflows into Folsom, we've looked at the storage in Folsom, and then looking at how our region's diverters are impacted by these changes. So this is just looking at the information tabularly for these different scenarios based in categorizing them based on points of diversion, areas of diversion. So whether they're upstream of Folsom Reservoir, the American River, or the Sacramento River, and then looking at what those total under each of the four scenarios. And so not unexpectedly, you see that on average, looking at these on the average annual for all years within the simulation, that increases about 100,000 acre feet per year in surface water diversions due to growth. And then when we look at how that changes due to climate change, again, comparing the climate change scenarios with the growth scenarios, you see that then there's a reduction in available water for diversion for the region's diverters. A slight reduction for the moderate climate change, and then a larger reduction under the hotter, drier, severe climate change scenarios. And again, this is looking at the average, just the average annual. And so one of the things we wanted to do was look at how those trends change within the hydrologic year types for each of the four scenarios. So what this one is showing is the average surface water diversion for each of the water year types. So whether it was classified as a wet, above normal, below normal, dry, and critical. Within each of the scenarios, and just seeing how that water that's available for diversion changes due to that changed hydrology. And the important thing that we were looking at here is how much of a shift is there in the amount of surface water available for diversion and as represented by the model between a critical year and a wet year, and how that changes under these scenarios. And so when you look across the scenarios, you see under the 2020 hydrology, it's about a 20,000 acre foot shift due to those hydrologic changes. But going all the way out to the hotter, drier, it's a much larger shift in the amount of flexibility that is needed in the operations and the reduction in surface water availability. And that there is a change due to growth also. It's not as startling as the climate change scenarios, but there is a change in the amount of surface water that is available to the region within those different hydrologic year types within each of the scenarios. So that's just broken down there for your reference to see how that changes. So just again, that climate change increases the surface water variability in these scenarios. So then looking at groundwater, this is again looking at it in this tabular form in the 4 scenarios, and instead of breaking it down by place of diversion, it's looking at them by groundwater basin. So the CalSim model represents the North American and the South American subbasins, and just looking at how much water the model is estimating the region to be extracting under each of these scenarios. And one note is that within CalSim and within these scenarios, the demands for each of the scenarios are constant. So there's no conservation, there's no reductions and there's no conservation measures modeled at this point. And any of those changes in surface water are made up for with groundwater. The CalSim uses this as a way to meet demands. So not unexpectedly, there's an increase with those changes in surface water availability. There's also an increase in groundwater extraction. So growth results in these models about 30,000 acre feet increase on average of groundwater extraction. And then when you layer climate change on top of that, and we saw that change in surface water availability, there's an added demand on groundwater. So 20,000 acre feet under the moderate climate change, and then 40,000 under the more severe climate change. And so we don't want to get too into the details about the groundwater sustainability plans and the groundwater sustainability agencies. They've done a lot of work in analyzing and projecting future conditions and understanding current conditions. And we shared some of that information at our learning and engagement session in July, I believe. And as a lot of you are probably aware, the region has shown positive trends historically and currently, that as a whole, the region is shown to be in balance and there's gaining groundwater levels over time. But these increases in demand of groundwater are also included in the GSP projections and the GSAs. And when layering in climate change, they are also showing potential overdraft under future conditions, but they are also planning management actions to mitigate those changes. And we just want to leave that there because we're not looking at a groundwater model. And as we talked about at the beginning, COSANA and the GSPs are their own analysis, and we will be doing a more detailed comparison later. But today we just really want to focus on our results. So we just want to put that note there. And then just thinking of taking that information and the implications for the region, that the reduced surface water availability will call for flexibility in the future. Those shifts in the dry years versus the wet years. The increased frequency of critically low storage at Folsom will challenge current regional operations, and that continued active groundwater management will be a cornerstone of the water supply reliability under future conditions. So that's the end of this section. And so Holger, I know you had a question back a couple of slides, so please. And you're on mute.
You can stay on the slide. It actually talks about the same thing. And that is the increased frequency of critically low storage at Folsom Reservoir. Is that based on current dam operations or changes in management based on central tendencies? I mean, what does the model reflect?
Can you say that one more time? Sorry, I missed just the beginning of it. I'm sorry.
Are the projected critically low storage levels at Folsom Reservoir based or considering current operations of releases or future central tendencies, management changes based on central tendencies? What are they based on?
That's a great question. So it is, I will let Jeff explain in more detail if needed, but it is representing current operations, current regulatory constraints. Everything is represented based on current operations.
So with the central tendencies showing a 55 centimeter rise in sea level, that presumably would increase saltwater intrusion into the delta, which means to combat that, they would likely have to have increased freshwater releases, which would presumably exacerbate the storage issues.
Correct.
Yes.
Ugh, okay, thank you.
Yeah,
Yeah.
so all of the current water quality control plan in the Delta, all of the current biological opinions, all of that is included and sustained through all the different scenarios. You know, so that the model does reflect, yeah, as you're implying that there's going to have to be adjustments to the operations to cover those, but there's no adaptation in terms of changing of overall large-scale water management practices, you know, for the system. It's assuming the current north-south balancing between storage and current general priority scheme is maintained.
Thank you.
Paul?
Yeah, Holger, that's exactly what the model produces, is the result that is what you're talking about. The reason for the lower storage that's projected is because of trying to meet the salinity standards and other things in the Delta. So there are a number of caveats that are described in the EIR modeling appendix that would probably be useful to include in this report as well. I sent those to you guys. And those are the ones we've talked about, which are, and Jeff just alluded to them, that the model itself can't capture any changes in the regulatory regime or changes in the contractual allocations for during particularly dry years. And so that's exactly what happens though during particularly dry years. So unless you know what those changes are and can put them in the model, you can't really accurately model those. So I think we need to keep in mind that the results during particularly dry years from the model don't reflect reality. And so we just need to take everything with a grain of salt, so to speak. I did have a question about on the slide that you have the list of groundwater use by basin, that one. Yeah, so is this the North American groundwater basin pumping? Is that for the full North American groundwater basin or just the Sacramento County portion?
This is the municipal pumping within the groundwater basin. So this is not, the agricultural water pumping is not reflected here. This is just our M&I. So, but it is, it's the groundwater pumping for the American River water purveyors, the municipal water purveyors.
So it goes beyond Sac County.
Yes.
Okay, so it could go beyond Sac County, but it doesn't include the agricultural use in Sac County. So you can't really directly correlate this with the sustainable yield that's listed in the groundwater management plan. Okay.
Correct. Yeah.
So it wouldn't hurt to relabel the slide, get M&I in there.
Yeah, we have it here, but we can make it more prominent.
Okay, thank you.
Yeah. Okay. Thank you all. Any other?
One thing I just want to add and kind of layer on what Paul was just saying is, and one reason we haven't, when we talk about the low storage, we didn't get into more detail about that because the model, as Paul's implying, is just that. It's just a model and it's based upon rules. And so the actual, we want to talk about frequency of those critically low storage as an indicator of periods where there's going to have to be some sort of active management and likely revised and something non-standard management of storages and operations. We saw that this year. We saw that last year. We're seeing that sort of operation. And so sometimes if you look too closely at exactly what the model is telling you, it can be misleading because you could say, wow, we're seeing a dead pool and all these years. Like, well, we're seeing that that's a possibility without some sort of intervention. And so that's I just kind of wanted to really put what Paul said about using a grain of salt, particularly in those really extreme conditions, is a really important thing to consider.
Mhm. Yeah.
And Ron's going to talk about settlement contractors. Is that what?
Exactly. Yeah. Yeah. To give you an example of a very significant change in operations this year is the settlement contractors, which use the lion's share of water in the Sacramento Valley, took an 18% supply this year, and their contracts call for reductions no greater than a 75% supply. So there was a lot less rice grown in the Sac Valley this year because of unavailability of water and essentially the requirement to take some extraordinary measures. And they're the folks who have a considerable majority of the amount of water in the Sac Valley. So thank you for channeling me there, Jeff.
It's a very important point.
Important, like, reminders and framing as we look at these results. All right. With that, we can move into the river health from a fisheries perspective, and I will. Yeah.
Actually, I just want to throw in here too, because I want to make sure that people are tracking. This is going from like highly technical, but we're hoping that it's kind of boiling up. So if you're sitting here like, my God, I have no idea what folks are talking about, raise your hand, let us know, send us a chat, and we'll either circle back or we can, we can work through this more. It is really important that we all kind of have a common understanding of this going in. And I just want to say too that we are planning on spending some time with caucuses going through the details of this, and there will be that study plan report that comes out that has additional details. So this is not the only bite at this information. We're going to be talking about it a lot as we go. The one other thing that I want to say is that each of the caucuses, when you put together your interest statement, this discussion around water supply reliability, climate change, groundwater, conjunctive use, surface use or surface water, and then here river health and fisheries. These were all really core interests in your interest statements. And we'll talk more about how we kind of bring those things together. But across the board, across all the caucuses, these were things that were really important. Okay, back to you, Ashley.
Yeah. Yeah, okay, so looking at river health from this fisheries perspective, this is for today, we're strictly looking at temperature results. As Jeff said, we had the HEC 5Q model in order to analyze the temperature, potential trends and impacts of temperature in the future. In the coming weeks, months, we will have additional analysis to inform to this question of river health for fisheries. And we're also planning to prepare some results for non-fisheries corridor health type metrics for recreation and aesthetics and other ecosystem functions of the parkway and the river corridor itself, recognizing that the co-equal objectives are not focused strictly on fish. But today, we are just going to be looking at the temperature results as they relate to the health of fish. And so looking at that, one, we see that growth and climate change reduce storage in Folsom. We looked at that in terms of a water supply reliability. We're going to be looking at that in terms of fisheries health and the implications for temperature. And that growth has minimal impacts on the suitable temperatures for fish, and we'll look into the details on that. But climate change severely is detrimental to fish in a very extreme way in terms of temperature. So we'll look at that in more detail. Before we get into our model results, just to make sure that there's an understood relationship between Folsom Reservoir storage and temperature, this is looking at historical end of May storage. Sorry, do you want to say something? Anybody? No, I thought I heard something. And degree days above suitable, which is just a measure of temperatures exceeding a certain threshold, which we'll talk about. But it's essentially looking at high temperatures correspond to low storage. So when end of May storage is low, the season typically has high temperatures in the river. So this is an important relationship as we look at these results. So looking at our model results and storage, Jeff, did you want to say something? I just saw you take yourself off mute.
Yeah, I was just gonna say, I wanted to go back, this slide. So, and this is using historical data. What we looked at was this, and we'll get into this degree days above suitable, exactly what that means later on in the presentation. But this is a really important point here, is that we saw there's a really high correlation between storage and degree days above suitable. You know, correlation's not causation, but just that they're highly correlated. And in May, more so than other months. And so what we saw is that May storage, both from perspective of cold water pool availability, and typically your highest storage of the year is sometime around in May. But that May storage really was a great canary in the coal mine when it comes to how suitable the temperatures are going to be for fish freeze later in the year.
Yeah.
So that I wanted to put that out here.
Thanks. Thank you, Jeff. Okay, so then looking at our results in terms of how the Folsom storage, the resulting Folsom storage throughout the year. And these are looking at this chart on the left is looking at the median storage for each month of the year for each of the 4 scenarios. And you can just, you're seeing that trend, and that severe climate change results in consistently lower storage. The current conditions versus the growth condition, it's up in the early parts of the year. In the spring months, they track closely, but there is slight separation as you move throughout the calendar year. And what this translates to, if you take the differences between those median storage values at the end of the month, for one due to growth, which is what this blue bar is showing, that change in median, and then the red and the gray bars are showing the change due to climate change for each month within the year. And then we look at May, and you can see that growth, while it does impact storage, we're seeing here it's not impacting that May storage, and so we would correspondingly expect it would not have an impact on temperatures. But the climate change scenarios have a pretty big impact on storage in the month of May and throughout the rest of the year. What you can see in June, there's a very big drop in the available storage, up to 300,000 acre feet lower storage in terms of the median. So that's looking at the storage. Looking at the temperatures for each of the 4 scenarios. This is again looking at the median water temperature for all 4 scenarios throughout the year, and it's putting it in relationship to the suitable temperatures for fish. And I'll just say that the suitable temperatures are based on the life stages of the fall run and the steelhead in the Lower American River. So they have different needs and at their different life stages. And so there are these kind of thresholds with which we try to stay below so as not to harm the fish. And what you see just by looking at these medians is that when we get to the climate change scenarios, there are 4 months when the temperatures are routinely expected to be above that suitable range. And again, just as Jeff explained earlier, what the median is that means that 50% of the time, there's 50% of the time it's greater than this value, but it is also lower. But it's a significant amount of time spent above that suitable range for fish. And when we look at the current and the growth scenarios, you see that, you know, we track pretty closely to those suitable ranges. There are periods where it's above, but it's not these like head and shoulders above that we're seeing with the climate change scenarios. So this is one way to look at it. And then as Jeff said, we have this other metric, this other way of looking at temperatures, and that is the degree days above suitable. And we just wanted to provide a little background on what that is so that we can understand the other results. So it is a cumulative representation of temperature effects. So it takes the difference between the suitable temperature and the simulated temperature, and then totals it for each day, and then it just adds that up throughout the period that you're looking at, whether it's a month or a year. So just a table down here as an example of these 3 days with these departures from the suitable and the simulated, and what that totals over that time. So then looking at results for this, that type of a metric for our scenarios, looking at the current conditions, projected growth, and the 2 climate change scenarios, you see these differences. So as we saw in that chart of the medians, there are periods when the current conditions and growth scenario are above the suitable range. And so you see these red and blue bars representing that. And so there are periods when that is happening. But when you get to the climate change scenarios, so the purple and the gold bars, these become much bigger and much more frequent. So there's months where that previously wasn't happening, where that is becoming a problem. And just a way of looking at that is that the big bars represent very unhealthy fish. If we're looking at the month of October as that peak, that there are 200 degree days above suitable within a 31 day month. So you're looking at upwards of 6 to 7 degrees on some of those days above the suitable temperature on average or on median. I'm not sure what the right way to say that is. And then just to put it in tabular form for a total for the year, this is looking at the median days above suitable just as a reference for each of the 4 scenarios, and then what that translates into the degree days above suitable. So these days are just saying, was it above that suitable temperature? Yes, so it's counting it. Whereas this is then getting into that severity. So looking at, like Jessica was talking about, frequency and severity. So this second column is providing a better indication of the severity and how far the separation is. And just one more note, just to make sure everyone sees, I don't know if it can see it on your screens, but if degree days above suitable is 0, that means that the temperatures are remaining within the suitable range for fish. Yeah, and the implications for the region are that actions balancing beneficial uses of available surface water will be necessary under future conditions. That if the fish are going to survive in the river, that there will need to be actions taken to manage the temperatures. Ron?
Just once again, revisiting the various measures of central tendency. Median means that 50% of the years, it's worse than shown on the slides.
Mm-hmm.
So just so when you're talking about fish health, that 50% can be rather important.
Mm-hmm. Yeah. Yeah, this is not right now. These results aren't looking at the most extreme conditions within each scenario. This is looking at the median, and that there would be 50% that would be worse than this.
Mm-hmm.
Yeah. Rob? I mean, you're on mute.
In terms of the temperature suitable for fish, isn't there a distinction between, there will a temperature beyond which there will be impacts on the health of the fish, and then a lethal temperature for fish?
Yes.
And I'm assuming that you're looking at the former situation. Have you modeled or done anything with the frequency of lethal temperatures?
We have not. That is a good suggestion, though. I don't know, Jeff, I saw you go off mute. Did you want to?
Yeah, I mean, there are a range of different analyses that we would like to look at. Like, one thing we could, for example, look at is what sort of range of habitat is available at suitable or temperatures, because this is at Watt Avenue we're looking at here, by the way.
Mm-hmm.
So it's possible there is some suitable temperature for somewhere upstream, but we haven't done any work yet to trying to quantify how much habitat at suitable temperatures would be available, and how much, if any, habitat's available at sublethal temperatures. So there's a whole range of different analyses that could come out of this that we haven't really gotten into.
Yeah, but the spatial distribution of those conditions is one, as well as, I think, adding in that lethal threshold.
That was going to be my follow-up question. Yes.
Okay, thank you. Tony?
Actually, to Ron or Robert's point, if you can go back to the frequency
This
chart.
one?
Yeah, but just something as simple as count days above a threshold is actually a very easy way for at least me to interpret results. So thank you for how this is presented. But to Ron and Robert's point, the suitable criteria appears to be kind of squishy, because right now, even in an average year or a median year in October, we're exceeding that threshold. It looks like about 40 or maybe 30 days Wait, so does that mean all of October we're exceeding that? Because there's only 31 days in October. Maybe I'm not understanding correctly, but I guess my point was, do we need to rethink the criteria that we're looking at there? To just make sure to help guide our policy on where we need to get to, right? The problem with ambiguous criteria is I don't know what the goal is then. If we're already exceeding it, and I know that our fish populations are struggling, but it's unfortunately just doesn't create a clear target for us on where we need to get to. And so I'm wondering if there's a better way to help steer our policy decisions, but by setting a little bit more clear target of where we need to get.
Tony, I just got to jump in. Yes, routinely we exceed the target temperatures at crucial life stages in the lower American River, such as October, when the fall run Chinook are returning, which is the dominant Chinook species on the river. And I think that does explain to some degree why fish populations are struggling and have been for so long, because in the modern era, and that is before the San Luis unit came online, or sorry, after the San Luis unit came online, we are routinely not creating what is judged to be suitable habitat temperature conditions for salmonids. And I guess we could try to refine, I mean, it's not our job. To some degree, it's reclamation and NOAA Fisheries and Fish and Wildlife Service to, if you say, well, we should probably refine our temperature objectives, and that may be an interesting exercise and perhaps even useful. But I think we do have a correlation between unfavorable temperatures, particularly in August, in October, and declining fish populations overall over the last few decades. And I'm just a botanist, but I talk to fish geeks all the time.
And I would just to say, especially on these results, to remember that these aren't predictive. These are the results of a HEC 5Q model, and with these being comparative, and just keeping that in mind. So like you're saying, with the current and projected conditions showing that we're already exceeding those temperatures. And as Ron is saying, that is true. There's oftentimes in the year that is happening in reality, but this is a representation based on this model. And then the thresholds, yeah, I think maybe some more discussion around that will be helpful. And I'm guessing Erica wants to add on here, maybe. I don't know, Tim, is your comment related to this topic, or is it something different?
It is. I just want to be sure that I'm understanding it. When I look at the graph that's on the right under severe climate change, I take the 624 and I divide it by the median days. So that's telling me that during this period, we are averaging 3.5 degrees above suitable when this is happening.
Yes, that's right.
You want to go back a slide, Ashley? Show that previous slide. It shows that.
This one?
This one here, yeah. Nope, go back one more. Yeah, so you can see here in October, this is a 5-degree grid, and you can see where that orange line is out there in October, for example, and you can see that it's this is the median, and you can see how far it is above that suitable line.
So in trying to understand the graph that's back to that right there to the right, where
this table, you
the
mean?
observation was, for October, if that's a cumulative of 200 median degree days above suitable, dividing that by 31 then would give us 6 degrees plus.
Yes. that's
Am I
right.
interpreting that correct?
Yes, you are.
Okay, thank you.
Perfectly.
And we don't give any credit for being below the threshold. That's the other thing. Below the threshold is a 0, so you don't get you don't get degree days above suitable off for
No offsets.
yeah. It's the
Yeah.
cumulative of the positive values.
Yeah. Erica?
Thanks, Ashley. I wanted to follow up on Rob's point and his question about the suitability and is there a range there and what's going on there. And, you know, Rob, that's a really good observation that we do have a gradation of temperatures at which we see different effects at different life stages. So it may be fine at one temperature, then we start to see some stress and some behavior changes, potential effects to fish health. And then you get into lethal temperatures or, you know, acutely lethal temperatures or temperatures that are lethal after a certain amount of time. And that's a spectrum. And that also affects our, you know, our fish that are coming in, you know, to Ron's point, when we're looking at fall temperatures where we're often not having suitable conditions for our fish. They're also running a gauntlet of other unsuitable conditions, you know, farther down in the Delta and in the South River. So the Jeff and Ashley's results here, or the Ad Hoc Tech Team's results here, are really focused on the Lower American. But, you know, as we get into working groups, well, yeah, that's something, just a food for thought, thinking about how far out, how far out of our Lower American can we look and what those effects might be, and just taking that all into account and where nodes may be turned. So good observation, Rob.
Yeah, thanks, Erica. All right. Any other questions or comments on the temperature results? Okay. All right. So then we're just gonna review the implications all in one place again. We've talked, this will be we've heard these a few times, but just to make sure we're all on, remembering kind of what we saw. So that for those hydrology implications, that the region's going to be in drought response mode more often, extreme and infrequent will become more common, and that those current operations may not be as effective under current or future hydrologies. From the water supply reliability perspective, that the reduced surface water availability and variability will call for more flexibility in the water supply management. Folsom Reservoir will be critically low more often, and that will challenge the current regional operations, and that the continued active groundwater management is incredibly important for the region going forward for water supply reliability. And then lastly, that fisheries implication that actions balancing beneficial uses of available surface water will likely be necessary. And I would just like to say, in reviewing these again, in that the charge of the Ad Hoc Tech Team and looking at this gap analysis was firmly in the realm of quantifying and understanding gaps and problems in the future. Looking at these implications, we're trying to be careful at this stage of the Water Forum 2.0 process not to talk about solutions. We're looking at kind of just trying to frame up that discussion and what those implications might be. But at this stage, we're not at that point of looking in detail at solutions, and that's what the working groups will be about. And so we're going to get to that topic next. And if there aren't any, we've talked a lot about it. If there aren't any comments or questions, discussion around the implications, I can go into next steps for this work. Jessica, go ahead.
Yeah, thanks. And Ashley, I think before we get there, this is a lot of information. I just wanted to throw it out there and see if folks want to repeat back things that we've heard. What are your main takeaways from this? Was there something that you heard that was surprising? Was there something that you heard here that you're like, oh yeah, yep, this checks out with all the other studies that we've been seeing? I'm just curious where you all are and what you're thinking. Ron?
I was going to say that that I appreciate the at least in model world attempt to quantify this data you know, most of us understand, or probably all of us understand qualitatively what the challenges are, but to have at least some degree of in the ballpark numbers is helpful.
Mhm. Thanks, Ron. Anne, and then Tony.
So super great presentation. It really helps frame the issue for, I think, the big picture stuff. I did not understand all of it, but I will eventually. The thing that jumped out at me a little bit was that 4-month shift under the worst scenario for flood ops. That's just like, wow. I don't even know where to start with that one. So yeah, a little shocking. But anyway, so that was my impression. Thanks so much for the presentation.
Thanks, Anne. And for all of us non-engineers, like I've seen this probably about 10 times. It's sinking in. Yes, every time you see it, it's more, there's more and more understanding. Tony, and then Marcus.
Thank you. So personally, as we've talked about Waterform 2.0 over the years now, sorry to say it that way, but it is, this is the place where I wanted to get to. I think the value of the Waterform is working together to solve common problems and, you know, get to, you know, our unique outcomes where we can work together. And I think the challenges ahead of us here in the 2020s are different than they were in the 90s that led to the to Waterform 1.0. I wasn't there, but I've heard the stories of lore. So I'm curious to ask Ron a question, since he kind of just I think offered praises for, you know, quantification of things. I'm curious from the environmental caucus perspective, if you feel you can speak for the group, do you feel like these results provide a kind of a baseline that we could start to lay out, you know, discussions and solutions around? I mean, do you feel like we're there in terms of identifying common problems?
Tony, I'm not so sure that I can distill everything for the group, but my perspective is this is a useful basis for discussions. It doesn't quantify the effective mitigation approaches. So, you know, that's obviously going to be important to understand. I mean, you know, what things we can do and how effective they might be, and partially or even completely mitigate these problems. But as I said before, I think this is a useful threshold step. And as the working groups and others amongst us try to grapple with these issues, I think we'll necessarily have to dive deeper than the presentation that we had today, but still useful. And I'm sure Clyde will opine. Remember, he's the engineer in the Environmental Caucus, not me.
Yeah, I would love to hear Clyde's thoughts on it. I only called on you because you'd already spoke, but yeah, I agree. Thank you, Ron.
Clyde, do you want to add on to the question to the Environmental Caucus, or is it, I don't want to jump Marcus and others, but.
Sure, I'll comment. I think having quantitative data is essential to finding a solution. I mean, for example, if we had gone through and said, well, gee, temperatures are going to get hotter in the summer, what would we do about it? How I mean, it's unless we know how much it is, then I don't think we can really solve these problems. The same thing with the water supply. Gee, Folsom is going to be, we're going to have more drought periods. But without a quantification, I don't know how you really deal with it. What is the magnitude of that problem? And I think that's what this quantitative data provides us, a kind of a way of looking at the severity of the problem or the lack of severity of the problem, rather than just, well, it's a problem, but we don't know what it is. So I think it's essential to allow us to go forward. So I very much appreciate the data.
Thanks, Clyde. And actually, I just want to jump in there because there's two sort of concepts that are coming up here. One around identifying solutions and then identifying sort of mitigation or level of impact of those solutions. And that's a really important concept. When the ad hoc tech team, we were very explicit about we're not talking solutions. We're really just defining the problem and staying in a space where we're trying to identify the gap. All that solutions work, which is fun and we all want to get into, is going to be in the working groups where we're starting to work through it. The ad hoc tech team, which will be less ad hoc by that point, but still this standing group will help, will be available to help analyze and quantify those solutions. The other piece that I want to just call out is this idea of metrics or criteria. That is a really important concept. And I think this work starts the body of work to look at, how do what are metrics of success for the region? But again, that's going to be, we're starting the quantification, we're starting to get a baseline as we go through the working groups, that those metrics are going to continue to be important as well. Sorry, jump in there.
Okay, Marcus.
All right, thanks. And thanks for the presentation. Just two quick items, and hopefully they're easy to do, or maybe you're already thinking about it. On slide 10, you discussed the other studies and some of the assumptions. Is part of the final report, would you be able to put together maybe a little table or something that shows what some of those key differences are? I think it just makes it easier so that we don't have to go try to find it. Maybe I'm just being lazy, but I would ask for that. And then on slide 15, where you're looking at the runoff, the occurrence of the runoff happening sooner, is the final report, or will there be some discussion as to what quantity of volume that is, or what volume that is, if it's different, the same, just to give an idea of if we are seeing runoff, just the magnitude of what we might see earlier relative to where we might be able to put that water. Thanks.
Yes. Yeah, thank you, Marcus. And yeah, I'm realizing as we've gone through different iterations of this, we did have that quantity of runoff, at least from an annual perspective, that fell off of this slide. But that is something that we will definitely include in the final report and any subsequent presentations.
Thank you.
Thank you. Paul?
So I think this is all useful information. I think we all have to remember that even from the most fundamental component of this, which is the global circulation models and the representative concentration pathways, that there are many assumptions built into those, and those projections may or may not come true. And then we keep layering on top of that all of these other modeling results. So it's good information. We in the water business are in the business of trying to predict risks and trying to mitigate those risks. And so we do that in our urban water management plans. We do that in our capital improvement plans. And so we'll be doing that as part of this dialogue. And this is useful information. And we all need to keep in mind what the caveats are, but I think it's going to be helpful in our discussions. And you got to keep in mind, these are just projections. So when you're looking at numbers, they're estimates based upon estimates. But in that context, it's helpful.
Yeah. Thanks, Paul. Ted?
Yes, thank you. I wanted to also express my gratitude for all of the work that's gone into putting together a sound technical basis for us to move forward into the discussion of alternatives. I hope that as part of that, we recognize on the one hand that there are differences of opinion in terms of climate change and how severe it might be in the future, but that as a group, we recognize the importance of considering the worst case as well as the more moderate case in our thinking. Secondly, I'd like to bring up the importance of groundwater, and a lot of our focus is on surface water, understandably, but I do believe that in as much as we're pivoting here, even on this chart, in terms of the importance of groundwater management and the future groundwater supplies, that we pay attention and reach out strongly to the GSPs, or through the GSP process to the GSAs, and involve them where we can in balancing this important question of surface water and groundwater, how they interact and interchange, and how they come together to allow the region to plan for sustainability. Thanks.
Yeah, thank you. Thanks, Ted. Kathy?
I was just wondering if I can please see slide 33 real quick. Thank you.
Yeah, of course. Just, yeah, okay. Did you have any questions or just wanted to see it really quickly?
That was it. Thank you.
Okay, very good. All right. Thank you all. I think that, Jessica, did you want to?
Yeah, no, thanks. That really helps us, sort of that kind of feedback. And should we talk about next steps?
Yes. Yeah. So as I mentioned a few times, there are other analyses that will be done in support of this initial gap analysis for the fish, specifically for the fisheries health, and one of those will be habitat availability. That should be forthcoming soon. And then also looking at some of the non-fisheries river health indicators. So that's stuff that will be coming out soon in the next couple of months. And then with that, there will be follow-up presentations and workshops. We've talked about potentially doing deeper dives into different pieces of these results and the analysis for based on people's interest, whether it's by the caucus or other groups, working groups. The details of that haven't been worked out yet. And then ultimately, as we've said a couple of times now, there will be a final report that includes all of that. That will in the background and how the analysis was developed and the assumptions that go into it. When we set this target of presenting in September, I think we said initially that there were some questions as to whether or not we would get there in time. So even though some of the analysis that we would like to do are not ready for this presentation, we still wanted to make sure we came with some of the initial findings that are important to the group. So there will be more coming, but we wanted to do this today to show you what we have so far. Ted, did you have another comment, or is that an old hand?
I'm sorry, I'll lower it.
Okay, no problem. Rob?
Yes, I'm wondering whether you have a time frame for the final report and whether you are thinking of a public release of the final report.
Yeah, I think that the time frame I hesitate to say something because some of it will depend on when the results are completed, but I would hope we would have it by the end of the year. And that because it was also, we'll be continuing to work with the ad hoc tech team on that and giving them the chance to weigh in. So we'll be hoping for the end of the year. And in terms of the public release, I'm going to look to Jessica.
Yeah, it's I think the end of the year is a good goal. We've got there's definitely a lot of information to distill. The original version of this presentation was 90 slides. So there's a lot more detail that'll go in the report, but we'll try and get that out as soon as possible. And I think this information, it won't go away after this presentation. You'll be seeing this information as we get into working groups and start looking at scopes. So it'll be pulled through And then the final, the report will come out eventually, but I think we probably still need a little work in order to give you a more accurate answer.
And believe me, we worked hard to get down the slide count with many hours of meetings just on that subject.
I do think it's worth serious consideration of releasing it publicly when it's ready to go out.
Absolutely.
Yeah, it would, just in terms of publicly, it would go on our website and then, it would be publicly available.
Okay.
Yeah, and
Okay. Very good. Yeah. So I guess the answer is yes, it will be publicly available. The when is a little bit more uncertain. I would say within the water forum, we're going to target for the end of the year. Ted?
Yes, thank you. It turns out I did have another question, and that is in the same vein. One of the things that ECOS does regularly for its full board is hold meetings and symposiums where we invite hopefully large groups of interested members of the community. And we would certainly be happy to sponsor a similar presentation with you jointly for this information. When you feel you're ready to present it, I'd be happy to take steps to publicize it as broadly as we can.
Yeah, that sounds
thanks,
great.
Ted.
Thanks, Ted. Tony?
I think it's time to show gratitude to the ad hoc technical team in some way. I'd offer up a retreat to our Hellhole Center. It's not as pretty up there anymore as it once was. I don't know, but in seriousness, I don't know. They've really done a lot here. I don't know. We should all think of a way to maybe just have a pizza party or something.
Oh.
Yeah.
Sounds great.
After 5 o'clock.
Yeah.
I like it.
I wholeheartedly agree. Thanks, Tony.
All right.
All right. Any other questions, comments? Yeah. Thanks, everyone. All right, let's do this. I think we have all earned a break. Let's take 10 minutes and then come back. That means you'll all come back at 11:15. Does that sound good?